Okay, so I hit the wrong button. I stopped that recording, so we'll just do a whole new recording for natural base and compound interest. That's okay. This tells us that many real-life situations can be described using exponential functions. We're in the middle of the pandemic, COVID-19 pandemic in spring 2020, and you guys have seen a lot of exponential increases on the news as they talk about how quickly the virus is spreading and how many positive cases we are getting. There will be so many mathematical models that come out of all this data that is being gathered. Exponential functions can model population growth for people, animals, microbes, illnesses, growth of epidemics, right there, that's us, radioactive decay, other changes that involve any kind of rapid increase or decrease. Sometimes these changes are modeled using what we call the natural base. Now, the natural base is an irrational number e, like pi. Pi is another irrational constant that you're familiar with. Find e on your calculator. If you look at your calculator, find natural log, ln, and that second function right above it is e to the x. That is where I'm going to find that natural base e. If you will turn on your calculator and hit second function natural log, and then push 1 for your exponent, this is a rounded off approximation, because I ran out of space, of what e is equal to. Just like if I had done pi to the first, it would be 3.14, etc., till I ran out of space. E to the first, just e, is 2.7, almost 2. We're going to round it off to 2 decimal places. So e is approximately 2.72. Oh, what is the other irrational constant found in your calculator? That one is pi, just like we mentioned, and we round it to 3.14 generally. Okay. We're going to use e when we are modeling some of these problems that use exponential, or examples of exponential growth and decay. For example, the cost of a family's health insurance X years after 2000 can be modeled by this function g of x, where my exponent I've got 6,875 times e to the 0.077x as my exponent. What was the cost for health insurance in 2011? Well, how many years after 2000 is 2011? That's 11. So that is going to be my value that I use for x. So x equals 11. This is just a calculator math problem. I'm finding g of 11 because I'm interested in the year 2011. That is 6,875 times e to the 0.077 times 11 as the exponent. Now we're going to round that off to the nearest penny because it's a cost function. When you have your calculator, you're going to start with e. Don't start with the 6,000. Start with e. So second function, natural log, brings up e to the, and then inside those parentheses, you do 0.077 times 11. I'm going to close my parentheses. And once I have that, I multiply it times the constant, that coefficient 6,875. So I find that in 2011, the average cost for a family's health insurance for a year is $16,036, and we're going to round that to the nearest penny, 89 cents. So $1,636.89. What would the cost be this year in 2020 according to this model? Well, I'm changing my variable, my input. If it's 2020, we are now 20 years after the year 2000. So we need g of 20. I input that into my calculator the same way. And you should get a cost of $32,069 and round it to 6 cents. Rounding matters. Make sure you round it to the closest penny. Another type of problem that you're going to find is compound interest. Compound interest, we have 2 different formulas for it. General compound interest or our compounded continuously formula. 2 different formulas. Compounded continuously is a little simpler. It is principal times e to the RT power. Now, P, R, and T, those variables, and A all stand for the same thing no matter which formula I'm looking at. A is my total amount. A is my total amount. P is the principal. If we're investing, it's the amount that I am investing. If we are borrowing, it's the amount I'm borrowing, but that's P. R stands for rate, as in interest rate. It's given to me as a percent. I use it as a decimal, so make sure you turn your rate into a decimal. N, I use an N over here in the compound interest problem. I don't use N when I'm doing compounded continuously because I'm compounding it all the time. Continuously is anything more frequently than daily. N is the number of times compounded a year. Per year. Now, this makes sense. If they tell you that something is compounded monthly, N would be 12. If they tell you that it's compounded quarterly, N would be 4. If it's compounded daily, we're going to use 360 because we go by the banker's rule in the United States, and it tells us that we're going to have a standard number of days in a year, not where you have to worry about leap years or anything like that. I don't think the book is going to give you any compounded daily problems. It's mostly going to be monthly, where N is 12, quarterly, where N is 4, semi-annually, where N is 2. Over here for compounded continuously, I've just got principal times e to the rate times time. That's my last variable. T is the time or the term of the loan or the investment. Let's do one so that you can see how this all fits together. If you're given $10,000 by Aunt Gerda and decide to invest it at an annual rate, R, of 5.5%, so P is my principal, that's how much I'm investing. R is my rate. How much money will be in the account after 5 years? That's T. If it's compounded monthly, that is N. So it's not compounded continuously, which means we're using this first formula. The amount in the account is represented by P times 1 plus R over N to the NT power. Let's plug in everything that we know. Our principal is 10,000. 1 plus our rate is 5.5%. I turn that into a decimal. It's 0.055 over N. N is the number of times compounded. We are compounding monthly, so N is 12 because there are 12 months in a year. Raised to the NT power. Well, N is 12, and we're leaving it alone for 5 years. So my exponent here is 12 times 5, or 60. Okay, I'm going to show you how to plug this one into your calculator. We're going to start on the inside. We need to follow our order of operations. So we're going to work inside our parentheses first, find that value, raise it to the exponent, get that result, and multiply it times the principal. So I'm going to start right here with this ratio. So I have 0.055 divided by 12, enter. And then I just use that answer and say plus 1, enter, and that's the amount inside my parentheses. So I need to raise that amount to my exponent. Remember we said that our exponent is 60. 12 times 5 is 60. Enter. And I take that and multiply it times the principal. So if I invest $10,000 for 5 years at 5.5% interest, compounded monthly, at the end of those 5 years, I will have $13,157.04 because we round it to the nearest penny. So my result is $13,157.04. I've earned more than $3,000 worth of interest. Okay, we have a couple of follow-up questions. Notice that the only thing that's changing is how often we are compounding it. For compounded quarterly, N is 4. Compounded continuously, I use my other function, my other equation. So let's do where we compound quarterly first. Compounded quarterly, same situation, $10,000 is principal. My interest rate is still 5.5%, transfers to 0.055, but now compounded quarterly, N is 4. So my exponent now is 4 times 5. My exponent is 20, not 60. So I start inside my parentheses again with that ratio, 0.055, this time divided by 4, plus 1, raised to the 20th power, and then multiplied by my principal. So not quite as much interest, but close. Still more than $13,000. At the end of 5 years, compounded quarterly, I have $13,140.67, if I round correctly. Okay, what if it's compounded continuously though? If it's compounded continuously, we use the other simpler formula, P times e to the n, let me rewrite that. A equals P times e to the RT power. That's my compounded continuously power, or formula. Principal, still my $10,000 Gerda gave me. Times E. R is still 0.055, and the term of the investment is still 5 years. When I plug this into my calculator, multiplying the e to the exponent first, and then I multiply that times my principal, the 10,000. I'm careful with my order of operations. I make sure that I get the correct answer out at the end. All right, into your calculator, you're going to start with e, so I need to do second function natural log. My exponent is 0.055 times 5. And then I multiply that times my principal, 10,000, and I get $13,165.31. So $13,165.31. A little bit better than when I was compounding monthly, but not a lot over 5 years.